Okay, good afternoon, everyone. Welcome to the PROSEC ML seminar. Today, we are very happy to have Amrita here. Amrita is now a postdoc at UCSD, working with Chowdhury. She graduated with her PhD from the University of Wisconsin-Madison, supervised by Sumesh Jha. Her work explores the synergy between differential privacy and cryptography through novel algorithms that expose the rich interconnections between two areas, both in theory and practice. She has been recognized as a rising star by lots of institutes and won a Facebook Fellowship finalist in 2021. Without further ado, Amrita, now the floor is yours.
Thank you, Rui, for the introduction. Hello, everyone. My name is Amrita Roy Chowdhury. And in this talk today, I'll be sharing my work, EIFFeL, which is a system for ensuring integrity for federated learning. This is a joint work with Chuan, Lawrence from Meta, and Somesh. Also, please feel free to stop me anytime during the talk to ask any question. So let's get started. Today, we spend more than a quarter of our daily lives online, connected via multiple smart devices. As a result, data is now born at the edge on all of these billions of smart devices in use. This has completely changed the mode of data generation. Every click, every like, literally every interaction we have with these devices constitutes a data point. Another interesting observation here is that these data generating devices have compute power. That is, they can support some data processing locally. With this new mode of data generation comes changes to our relationship with and understanding of the data. The generated data is personal and hence sensitive. The data is literally documenting our daily lives at a very close granularity, and this raises serious privacy concerns. To make matters worse, adversaries today are more powerful than ever, as is evident from the plethora of data breaches that we have seen in the past few years. One of the most recent ones is the T-Mobile breach, which is a multinational telecommunications company that happened earlier this year. And in this attack, personal data of 37 million customers were exposed. In the wake of such serious privacy breaches, government agencies around the world have formulated privacy regulations such as EU's GDPR and California's CCPA. These regulations make it legally obligatory for organizations to uphold data privacy. Parallel to the changes in data generation, the way we use and learn from the data has also changed. For this talk, I am specifically interested in the task of learning a machine learning model from the data. So now a machine learning model has to be trained on this massively distributed data. For example, consider a setting where every phone with a Gboard app is basically a source of data, and Google is interested in learning a model about next word prediction on the joint dataset of all of its users. An additional characteristic is that these datasets are constantly growing and evolving. Hence, the corresponding models have to be frequently updated. Further, as I just motivated, the training has to be privacy preserving. Thus, what we are seeing is that modern applications necessitate new learning paradigms. An upcoming answer to this challenge is federated learning. Federated learning is a decentralized learning paradigm where multiple clients collaborate with the server to train a model. Referring back to our previous example, here every Gboard user is now a client and the server is owned by Google, who wants to train a model on the joint dataset. An important characteristic of federated learning is that each client's raw data is stored locally and never exchanged or transferred. In other words, there is no centralized data pooling. Instead, clients perform local computation and send in focused updates intended for immediate aggregation. These updates are typically the gradients of the parameters of the model computed over the local dataset. The server uses this aggregate update to train the model. These steps constitute a single training round, and this process is repeated for every iteration. So, federated learning decouples model training and centralized pooling of data. This has a couple of advantages. First, data processing is also moved to the edges, which can have performance advantages such as improved bandwidth. More importantly, this setting is very attractive for an organization as they are now relieved of legal obligations associated with data storage, such as responding to a government subpoena. Now, let's understand the threat model here. First, the central server, which is say Google, is untrusted. So we need to ensure privacy of the client's inputs. It is important to note here that just decoupling the model training from central pooling is unfortunately not enough to ensure data privacy. Prior work shows that attacks can infer sensitive information about the inputs using just the updates. The common solution for this is to perform a secure aggregation of the updates. This is essentially a cryptographic protocol where the individual updates are masked and only the final aggregate is revealed in the clear. Now, on the flip side, the clients can also be malicious. The distributed nature of federated learning makes it vulnerable to poisoning attacks. It is extremely easy for an adversary to inject a bunch of fake users who submit poisoned or malformed inputs to the server. This compromises the integrity of the training phase. These poisoning attacks can be either untargeted, where the goal is to reduce the overall accuracy of the model, or targeted, where backdoors for some target class is injected. These attacks can be quite severe. In some instances, even a single malformed update can significantly alter the trained model. Hence, to ensure robustness of the trained model, we need to check for the well-formedness of the inputs. That is, ensure input integrity. In other words, we should be able to detect syntactically incorrect inputs. An example of a syntax could be that the input needs to be norm-bounded. This problem is especially challenging in the context of secure aggregation, since recall the individual updates are masked, thereby preventing direct audits on them. Thus, the ideal goal is to ensure both input privacy for the clients and input integrity to protect the global model from poisoning attacks. In other words, the major question now boils down to how to ensure integrity without seeing the input in the clear. Any questions so far regarding the problem setup? Okay, cool. The problems of input privacy and integrity have been well explored, but only in isolation. Prior work that addresses both privacy and integrity is very limited and suffers from a host of drawbacks, such as support for only limited integrity checks, or high computational overhead, or unrealistic threat models. To this end, I have proposed EIFFeL, which is a cryptographic framework that supports arbitrary integrity checks without violating privacy. This is the first general framework to do so. this is going to be the outline for the rest of my talk. I'll talk about EIFFeL's design, followed by its workflow and some evaluation highlights. I'll start with the problem formalization. In order to formalize the problem, first we propose a new protocol for federated learning, which we call the Secure Aggregation with Verified Inputs, or SAVI protocol. The server has a public validation predicate that defines a syntax for the inputs. An input U is considered valid and hence passes the integrity check if valid U evaluates to 1. Any per input robustness check from the machine learning literature can be a candidate for the validation predicate. For example, a predicate could check that the norm of the input is bounded. Another example of the predicate could be checking the cosine similarity between the input and a clean update computed from a public dataset. In a nutshell, a SAVI protocol securely verifies the integrity of each input and aggregates only the well-formed inputs. That is, the inputs for which we have valid U equal to 1. Only this final aggregate is released to the server in the clear. Now, it is important to note that there is a fundamental difference between just detection of a malformed input versus detection and removal. With just detection, the server can only abort the current round, even when just a single malformed input is detected. This makes it vulnerable to denial of service attacks, which renders the server incapable of training. However, SAVI protocols both detect and remove the malformed inputs, thereby allowing the server to train using just the valid updates. EIFFeL is a system that instantiates a SAVI protocol. Specifically, EIFFeL can support arbitrary validation predicates that can be expressed as an arithmetic circuit with public parameters. An arithmetic circuit is a way of representing computation. It is very similar to a Boolean circuit, but instead of OR, and NOT gates, we have addition and multiplication gates, and the computation is performed over a field. EIFFeL does so in the fully malicious threat model. Specifically, this is the strongest cryptographic threat model. Here, the adversary constitutes a set of malicious clients and the server. The adversary is free to behave arbitrarily and deviate from the protocol in any way they choose to. Moreover, they're allowed to collude together in attacking the honest users. Now, let us look at EIFFeL's design goals. First, EIFFeL should be flexible in terms of the integrity checks it supports. Second, EIFFeL should be efficient. Finally, EIFFeL should be compatible with the existing federated learning infrastructure in deployment. An important constraint here is that EIFFeL should be able to work with a single server, which characterizes a realistic federated learning deployment setting. Any questions so far? Okay.
Hi, I actually
Yeah.
have one question.
Yes.
I'm wondering what's the challenge when you're combining the privacy and integrity?
So the challenge,
because prior work, there is only limited work about the combinations. Yes, I'm curious why.
yeah. So the challenge here is again because the privacy is ensured by secure aggregation, which is a cryptographic protocol.
Yeah.
And because of that, these inputs are masked. So we have to somehow do these integrity checks on these masked inputs.
Oh,
So
I see.
so the overhead is basically, how to do checks over masked inputs, over using cryptography.
Actual data. Okay, I see. Thank you.
Yeah, okay. Awesome. So now let's look at the building blocks needed for EIFFeL. Here we use two cryptographic primitives, secret shares and zero-knowledge proofs. Secret shares is a multi-party computation technique which allows multiple untrusting parties to securely compute on their secret inputs. In this scheme, the secret or private input is split into n shares, one for each party. Any set of n-1 shares reveal no information about the secret. Additionally, the parties can perform linear computations on the shares locally. For successful reconstruction of the secret, one needs access to all n shares. The second primitive is zero-knowledge proof, which describes an interaction between two parties, prover and verifier. Prover has a private input U and wants to prove some statement on it, such as, in our case, the input is well-formed. To do so, it sends a proof pi to the verifier, who decides on the validity of the statement by analyzing the proof. At the end of the protocol, the verifier is convinced of the proof only if the prover's claim was indeed true. Additionally, the verifier learns nothing else about the private input. In EIFFeL, we use a specific type of zero-knowledge proof called Secret Shared Non-Interactive Proof, or SNIP. SNIP is a lightweight zero-knowledge proof that is optimized for the client-server setting, where the client is the prover and the server is the verifier. It uses multiple honest verifiers for its protocol. The original deployment premise for SNIP, called PRIO, proposed to use multiple honest servers to act as the verifiers for the client prover. SNIP works on a private data U that is distributed using secret shares. Specifically, the verifiers hold shares of the prover's private value U and proof pi. Additionally, the verifiers hold a public validation predicate, which is expressed as an arithmetic circuit. The goal of the verifiers is to test if valid U holds without learning anything else about U. For this, the verifiers check the validity of the proof by gossiping among themselves. Specifically, they generate random digests D of their proof shares and accepts the proof only if these digests satisfy a certain condition, which in this case is that they sum to 0. Now, I'll be discussing the key ideas behind EIFFel's design. Excuse me. For this, let's revisit the design goals of EIFFeL. As I have just discussed, SNIP supports arbitrary validation predicates in the form of an arithmetic circuit. So EIFFeL is flexible. First goal, check. Now let's look at efficiency. Again, recall that SNIP is a lightweight zero-knowledge proof that is specialized for the client-server setting. Hence, it is efficient. Also, the secret shares are used here just for the aggregation, which can be performed locally and is hence efficient. Second goal, checked too. However, when it comes to compatibility with existing federated learning infrastructure, we are faced with a problem. Recall that SNIP requires multiple verifiers. EIFFeL resolves this issue in the single server setting by making the clients act as the verifiers for each other under the supervision of the server. Specifically, when client I is trying to prove the validity of its input, all other clients J act as the verifier, and the server supervises the verification process. We are still not done here, though. The second issue is that SNP requires all the verifiers to be honest. However, as we have seen, EIFFeL can have malicious clients and hence malicious verifiers. Thus, EIFFeL tackles this challenge by extending SNP to the malicious setting by introducing redundancy in the verification process. EIFFeL uses a threshold secret sharing scheme, which is associated with the parameter threshold t. Here, any set of t-1 shares reveal no information about the secret. However, any set of t shares is now enough to reconstruct the secret. What this means is that any set of t clients can now emulate a SNP verification process, which results in redundancy. Any questions so far? Okay. So
Hello.
next, yes, yeah.
So I have a question now.
Yes.
I think this method is just based on the client as the verifier. So what if all the client are the malicious? So can
in this process, both the clients under the supervision of the server act as the verifiers. I will talk about it later, but in general here, we need to have an assumption that less than 1/3 of the total clients are malicious. So as long as the number of malicious clients is less than 1/3 of the total number of clients, we would still be successful.
Okay. Thank you.
Okay, so next I'll be describing the workflow of EIFFeL. First, I'll go over some notations and details of the problem setup. The number of clients in a single round is denoted by N, and M is the number of malicious clients. Here, the threshold T is set to be M+1. Additionally, every party has read and write access to a public bulletin board. In practice, the bulletin board can be implemented as an append-only log hosted at a public web address where every message and its sender is visible. EIFFeL works in 4 rounds. In the first round, all the necessary public information is announced. Specifically, the server publishes the validation predicate. The clients generate a key pair and publish their public key. Additionally, every client pair generates a common secret using the public information and their respective secret keys. The second round is the generate and distribution of proofs phase. First, every client I splits its input and proof into N shares, one for every other client. Next, it encrypts the shares with the corresponding common secret key and publishes the encrypted data or ciphertexts on the public bulletin. The verification of the proof happens in the third round. Here, the client J decrypts its share of client I's proof and input and computes the digest using SNP. Next, the server collects the digest from all the clients. Now, recall that since we use threshold cryptography, any set of T client is capable of emulating a SNP verification process. So the server samples multiple T-sized cohorts and verifies the proof for each of the cohorts individually, which is basically summing the digests and checking whether it is zero. The server then takes a majority vote of all of the outcomes and decide whether the proof is valid. The server makes note of all the clients with invalid proofs and publishes the list of such malicious clients. For instance, here the server marks the client I as malicious. The final round is for computing the aggregate. Here, the server instructs the remaining clients to send in their share of aggregates, excluding the values corresponding to the malicious list. The server computes the final aggregation by taking a majority vote over cohorts as before. Now, what I just discussed here actually gave a simplified and conceptual picture. Secret shares are closely related to error-correcting codes like Reed-Solomon codes. In the paper, we discuss a more principled approach for robust verification using Reed-Solomon codes and verifiable secret shares. Now, to see why this is a savvy protocol, first, privacy is ensured by setting threshold appropriately. Recall that for threshold cryptography, any set of T-1 shares reveal nothing about the secret. So if M is the number of malicious clients, and if we set T to be greater than M, say M+1, then clearly a collusion of M clients who have access to only M secret shares cannot violate privacy. Now, coming to the integrity constraint, it can be shown that the server returns the aggregate of only the well-formed inputs as long as the number of malicious clients is less than 1/3 of the total client size. Any questions so far about the workflow? Okay, cool. We also propose a bunch of optimizations to improve EIFFeL's runtime performance. I will not go into the details, but will give a brief overview of the key ideas. These optimizations can be classified into two types broadly. First, we propose probabilistic reconstruction. What this means is that instead of guaranteeing the exact reconstruction of the secret shares, now we might get an incorrect reconstruction with some small probability. This essentially translates to a small probability of failure in catching the cheating client, or the soundness guarantee of the zero-knowledge proofs. An example is that instead of checking the proofs of all T-sized cohorts, we can verify only for a strategically selected few. This reduces the computation overhead at the cost of a small probability of failure. We also propose several optimizations based on crypto engineering tricks to reduce the number of circuit computations. One such example is, in order to reduce the data dimensions, we apply fast random projection based on Walsh-Hadamard transform on the updates. This reduces both computation and communication overhead at the cost of a possibly slight loss in model accuracy. Hence, to summarize, EIFFeL is the first general framework to ensure both input privacy and integrity for federated learning. Its implementation is based on the SNP-proof system. However, the challenge here is that SNP requires multiple honest verifiers or servers. EIFFel's core technical novelty is to provide an efficient extension of SNP to a fully malicious threat model in a single server setting. Okay. Now, coming to the evaluation of EIFFeL, we evaluate EIFFeL along two dimensions, accuracy and performance. Our evaluation uses four popular machine learning datasets, MNIST, FMNIST, EMNIST, and Cypher10. And our prototype implementation uses Sameer's secret shares. We also use the Feldman's verifiable secret sharing scheme. We evaluated 6 poisoning attacks, ranging from the classic label flipping attacks to the state-of-the-art strong attacks such as min-max and min-sum attack and backdoor attacks. In order to demonstrate the flexibility of EIFFeL, we evaluate it on 4 validation predicates, such as checking the norm bound or cosine similarity. For our accuracy experiments, we test whether the proposed optimizations affect the efficacy of the validation predicates. We observe that EIFFel's training accuracy is comparable to that of a baseline that applies the defense on the plain text for most datasets. Coming to the performance of EIFFeL, we observe that EIFFeL has low computation cost. For instance, with 100 clients, out of which 10% are malicious, EIFFeL trains a model on MNIST to the same accuracy as that of a non-poisoned one in 2.4 seconds per iteration per client. The associated communication cost is also low. For instance, for the same example, the communication cost for the client is 13.3 MB. Our proposed optimizations improve the performance by up to 2.3 times. We evaluate EIFFel's performance improvement over a baseline prior work BRIA as well. BRIA employs a different approach for robustness and implements a secure version of the multi-crumb protocol, which is a robust aggregation protocol that detects outliers based on pairwise distances of the inputs. Nevertheless, we chose BRIA as our baseline since it has the closest fit with EIFFel's functionality compared to other prior works. We observed that EIFFeL is significantly better performant than BRIA. For instance, for MNIST with 250 clients, out of which 10% are malicious, EIFFeL reduces the computation overhead by 18.5 times. Now, coming to the conclusions, I will discuss some future directions to explore. An interesting direction is to integrate EIFFeL with differential privacy. Recall in secure aggregation, the aggregate is revealed in the clear. However, this aggregate itself can leak sensitive information, thereby violating input privacy. So we need to release a noisy aggregate instead that satisfies differential privacy. Specifically in EIFFeL, this extension can work as follows. When the clients send in the shares of the aggregate after the proof verification stage, they can add shares of suitable noise, such as discrete Gaussian, to it as well. Thus, the final aggregate computed by the server will be noisy, and this ensures differential privacy. The use of differential privacy here is actually a win-win situation for us, since prior work has shown that differential privacy can also aid in robustness against poisoning attacks. Another direction here is to improve the efficiency of EIFFeL further. So the dependence on N, the computational and the communication dependence on N, which is the total number of clients in a single round, can be improved to be a logarithmic one by using techniques such as threshold homomorphic encryptions. The idea here is that instead of having each client verify the proofs of all other clients, we can make them verify the proofs of only around log n clients by choosing their connectivity in a smart way. Another direction is to extend the support for other types of integrity checks, such as statistical tests like z-test or chi-square tests, or ensuring that the data satisfies the correct functional dependencies. So in summary, I have established why federated learning requires both input privacy and integrity. And I have discussed a system to achieve this called EIFFeL. EIFFeL enables a machine learner to employ arbitrary integrity checks on the individual inputs without violating their privacy. And EIFFeL is performant and efficient even in the fully malicious threat model. Thank you for listening to me today, and I would be happy to answer any questions you might have.